Aloha and welcome to another episode of The Physics Coach. Today we're going to solve a simple one-dimensional kinematic problem. Before we get started, I want to go over a few problem-solving strategies. And the first one is you always want to state your givens and define your variables and directions so that your problem solving is consistent throughout. You want to identify what the problem wants you to solve for. Do a sketch of the problem with variables if appropriate, and often a problem can be solved by doing a diagrammatic sketch. When you do the solution, you want to start with an equation or a law and derive it in terms of the variables. You don't want to start putting in numbers too early because often a mistake is made carrying numbers around. So solve for the algorithm. That's the most important part of any solution to a problem is the algorithm. After you've solved for the algorithm, then put the numbers in with the units to find your final solution. You check the units when you're done to make sure you didn't make a mistake. For students studying for the MCAT, this is critical. Unit analysis is very important for the MCAT and also for doing physics and science. You round your answers to appropriate number of significant figures. Often that's 3 or 2. And box your final answers. And most importantly, you want to be able to describe your results, if not in the solution itself, but in your own head, because we want to be able to go between the narrative of a problem, of a real world problem, putting that information into data, and then solving it using mathematics and the laws of physics. And neatness counts, especially to your grader. Here's the kinematic equations that Galileo defined and derived. We have the definitions at the top for average velocity in terms of displacement and time. Here's the equation for average velocity in terms of the initial and final states divided by 2. It's actually an average. And then the average acceleration, if you have a changing acceleration, will be equal to the change in velocity over the change in time. These definitions are always true, whether or not you have constant or a changing acceleration. If you have a special case of constant acceleration, then these equations are true. So you have an equation for the final velocity, the total displacement, and then this is actually an expression of conservation of energy. It's a squares formula is what I like to call it. Again, all of these equations can be used in either direction. They can be used in the X direction, the Y direction, or the Z direction. And when you get to rotational kinematics, there is also a version of these for rotations. So the problem we're solving is quite simple to start with. And the first thing we're going to do is read the problem and circle or identify, mark in some way all of the data. So we have an automobile entering a freeway on a ramp as shown in the picture at 15 meters per second. So what is that? That's going to be my initial velocity. So, and then it accelerates uniformly up to 25 meters per second in a time of 10 seconds. Okay, that's the problem. When I analyze the problem, I like to identify, what these numbers mean. So I'll make a note to myself that that's the initial velocity. Then what's this? That's the final velocity. And then what's the 10 seconds? That's the total time. So especially in a long problem, like you can go through and circle everything and then just kind of mark what the variables they represent are, because otherwise information can be lost. Another important piece of data is that it accelerates uniformly, and uniformly is code for constant acceleration. Now I write my givens out in a list to make it nice and neat. And so I can go back to this list and use it as needed. So I know what the initial, the final, and the total time are for this. So again, this accelerating uniformly means that it's a constant acceleration, and therefore I can use those special Galilean kinematic equations for constant acceleration to solve. And I make a note of that. So what are the unknowns? I don't know what the average velocity is. That's what they're asking in part A. They want to know what the acceleration is in part B. And then in part C, they're asking what the total distance traveled in this amount of time. Since it's a one-dimensional problem and it's only traveling in one direction, the distance is equal to the displacement, right? So displacement is a vector, distance is a scalar. But in this case, they're the same. So which equation will I use for average velocity? So we look at our equation sheet, which you can get when you're my 2D. I have all these documents on the website, so that you can use. So we look at this sheet and we say, okay, which equation should I use? So what you want to do is you look at what you know, and then you look at what you want. So the average velocity is in these two equations here. So I would need to know the net displacement and the change in time for the first equation. And I don't know the net displacement. I know the initial and final states of the velocity. So I can use the second equation. So that's what you do. That's why it's important to label everything. Otherwise, if you don't make that list of givens, then you're just looking at the equation sheet like, what do I do? What am I doing? I'm lost. I'm lost in a garbage can of equations. So that's what you do. And so I can use this equation to find what I need. Ta-da! All right, so let's go ahead and solve that. You write the equation out. I just like students to always write the equation before you put the numbers in, because it also, you can compare it against the equation sheet to make sure you didn't make a mistake writing it down. And then you actually memorize them after a while, which you may not need to memorize them, but it's useful. And I think on the MCAT, you're probably given some equations, but you just work faster if you memorize. So I put in the initial, which is 15. I put the units in, absolutely, to make sure that I get the correct answer, because I will do a unit check. So I add them together, and that's 40 divided by 2, or 20 meters per second. And that makes sense, because if you look at the numbers and you say, what's the average between 25 and 15? Well, it's 20. So there you go. And then you box it. That's the average. The bar means an average. Okay. Oops, I don't know why that went away. All right, so now I put that information down here because now I know it. And now I want to find the acceleration. So which equation? I go back to the equation sheet. Which one of these equations has the acceleration in it? Well, it's in this. So since it's a constant acceleration, the average is the constant acceleration. They're the same. So I can use that equation. It's also in these other equations. This first kinematic equation is just a rewriting of this average equation. So this one's more straightforward because I know the change in velocity, I know V final and V initial, and I know the time. So that's the most direct. I could use the top equation because I know everything there, but I don't know the displacement, so I can't use the second or the third equation on the bottom. So I think we're going to do both just to prove that you get the same answer. So I write out the equation, put the variables in, and I end up with 25 minus 15 is 10. 10 divided by 10 is 1 meter per second squared. Notice the units. I have meters per second over second, which is meters per second squared. Checkity, check, check. So I get the average or constant acceleration is 1 meter per second squared, which makes sense because the car went from 15 to 25 in 10 seconds. So that means every second it was gaining a meter per second of speed. Okay, so I guess we're just doing it with the one equation, since it's equivalent to the average equation is equivalent to the V final equals V initial plus AT. Okay, so which equation can I use now to get the average the net distance traveled, or the displacement? Well, displacement's in this equation. I think I can use this equation because I know the average and I know delta T. So I can use this, or I can use the second equation, or I can use the third equation. But honestly, which one's easier? Here I have to, in the bottom equation, I have to do squares. Here I have to use a square. I'm lazy. I'm going to use the equation that's the easiest. Now, is one better than the other? Not necessarily. Some students will use a different equation. It doesn't mean that it's wrong. They should all give the same answer. So I think that one's the easiest, but again, you could use that one and that one. So let's start with this equation, since it's straightforward as well, because it's just delta x is equal to this. So you put in all the numbers, 15 meters per second times 10 seconds. So this is another good reason why you want to write out the equation before you put the numbers in, because you can do a one-to-one check. Oh, I've got the velocity, I've got the time. Notice how the meters per second times the second cancels and you get meters. The number one mistake students use with this equation is dropping the time, this time right here, they forget. And then if you forget that and you don't do a unit check, you won't catch your mistake. And when you're taking a test and you're stressed, like, you want to make sure you have some mechanisms in place for you to check your work. The second mistake is dropping the half, like that. People forget that all the time. And then the other mistake is dropping the square. So anyway, 1/2, I got 1 meter per second squared times 10 seconds squared. So the seconds cancel, and I end up with 200 meters. 200 dot would makes those all significant. All right, so let's try the other equation. So I have the average velocity is delta x over delta t. So I do the algebra, solve for delta x, always put the variable you're trying to solve for on the left-hand side and work to the right. That's how math is done. It's clean, it's neat, you will make less mistakes. And then, so I have v average times delta t. Well, I know my velocity average because I calculated it in the first step. So I got 20 times 10 or 200. So that's much easier to use that equation and you get the same result. And just for the heck of it, you can also solve using the squares formula, but it's a lot more work. Again, you want to solve for the variable first in, that you're trying to solve for, delta x, in terms of all the variables. That's your algorithm. Put in the numbers and then solve, and you end up with the same result. Of course, you better end up with the same result. Sometimes when students are studying together and they're going over their work, one student will have used one equation and another student another, and just realize as long as you're getting the same result and you're using the correct equations, that, you know, it's all correct. It's just, you know, you have choice. How great is that? Well, thanks for joining me, and I hope you found this useful. And if you're interested in one-on-one tutoring, then check me out on physicscoach.com. Mahalo.